So when we're doing an ANOVA, we're really talking about the ANOVA table. And there are a few important elements of an ANOVA table that we should talk about. The first is the source. And you'll see later on the next page, actually, that the ANOVA table is divided into variation sources that represent the treatments and factors, the error or the residual, and the total variation. So you'll see that each row of our ANOVA table represents a different source of variation. And each of those sources have a degrees of freedom associated with it, a sum of squares, a mean squares, an F statistic, and a p-value. So that F statistic and p-value are what we actually use to assess the significance of the effect. So let's take a look at an example of reading an ANOVA. So this here is an example of a one-way, and we'll actually do this example with this data in our video next week when we go into one-way ANOVAs. But I just kind of wanted to show you this so that you could see what an ANOVA table looks like. So in this, we have, here, let me get the laser pointer out. Okay, so in this, we see that we have the source, degrees of freedom, sum squares, mean squares, F value, and P value. And you'll see that for a one-way, no matter how many different treatment groups we have, we will only ever have between, error, and total. That's because between is, that's evaluating the variation between each treatment group. And you'll see we have degrees of freedom of 3. So we'll get into the math later, but that means that we have 4 different treatments that we're looking at. Here is our sum squares, our mean squares, and then our F and P value. And we can use an F critical value to evaluate significance, but it's probably easier to use a P value because we know for our particular example, make sure you check with your organization, but we are going to use the standard 0.05 alpha level. And so this p-value is less than that 0.05, which means that we reject the null hypothesis. Here, the null hypothesis being that all of the treatment group means are the same. So if we reject that, then we can say that a factor is showing a significant difference from the others. Further testing is required. So all that a one-way ANOVA can tell us is whether or not one or more treatment groups are significantly different than the others. Now let's take a look at a two-way ANOVA. So in this two-way ANOVA, you'll see that we have factor 1, factor 2, and interaction. Okay, so factor 1, we take a look at our p-value. It's less than our alpha of 0.05, so we reject the null hypothesis. Therefore, the effect is significant. So the effect of factor 1 is significant. There's something going on here where different levels of factor 1 change things. So like let's pretend that that's a temperature. And let's say we find that lower temperatures lead to a maybe a higher hardness of our paint, whereas higher temperatures lead to a lower hardness of the paint after it cures. Factor 2, we see that there is no significant effect, that, well, at least we failed to reject. So at the 0.05 level, there's no significant effect. That means whatever pressure, let's pretend this is pressure, whatever pressure we're evaluating at, we're not seeing that affect the hardness of our paint. Okay, interaction. Let's talk about this one because in a two-way, we'll get into this more later. This is a big one. So we'll see here 0.81. That means we failed to reject the null hypothesis. The effect of our interaction is not significant. Now, if we were actually analyzing some data and not just using this as an example to show you what a ANOVA table looks like, we would rerun our two-way ANOVA without the interaction because this interaction effect actually does affect factor 1 and factor 2 p-values. It doesn't affect the sum squares or the mean squares, but it does affect our F and P value. We'll get into that in a couple weeks when we take on the two-way. But for now, this is an ANOVA table. This is how you read it.